Welcome to The Explainer. Today, we're zooming in on something that trips up so many people, mastering Apache Spark scaling issues. We're going to take a nice, slow, and deliberate approach today. We'll break down exactly how a true professional tackles massive big data problems step by step.
Okay, let's dive into this. Your application works perfectly at 10 gigabytes, but it fails entirely at 2 terabytes. Why? This is a classic interview question, but honestly, more importantly, it's a very real, everyday problem for data engineers.
Here's our roadmap for today. 1. The scaling trap. 2. The engineering mindset. 3. Fixing partitions and skew. 4. Shuffle memory and resources. And finally, the ideal interview answer. We're giving you the exact framework and vocabulary you need.
Let's start right off with Section 1, the scaling trap.
You see, there's a huge hidden danger in scaling questions. The trap is guessing. When faced with a crash, a junior engineer will almost always jump straight to guessing. They'll say, hey, let's just increase the memory. But a senior engineer, they take a totally different route. They say, hold on, let's identify the bottleneck first. Jumping straight to adding memory without solid evidence is a trap.
Which brings us nicely to Section 2, the engineering mindset.
Here is the core philosophy you really need to internalize. An application that works on 10 gigabytes but fails on 2 terabytes usually exposes scalability issues that were just hidden at a smaller scale. Think about it. Moving to 2 terabytes doesn't just mean your data is larger. It actually means the hidden underlying flaws in your code are finally being exposed.
So the crucial point is this. Your very first step has to be checking the exact error. You literally have to look at the logs and see what failed. Did it run out of memory? Was an executor lost? Did a shuffle fetch fail because the data just couldn't make it across the network? Was there a timeout? Look, without identifying the exact error first, any configuration tweak you make is literally just a blind guess.
Let's transition to Section 3, fixing partitions and skew.
So, step 2 is checking your partitioning. I like to think of partitions like breaking a giant meal into bite-sized pieces. Obviously, larger datasets require more of those pieces to stop a single machine's memory from just exploding. The really tricky part here, Spark might just default to the exact same number of partitions, whether your data is tiny or absolutely massive. Let's actually run the math on this because it's pretty shocking. If you have 10 gigabytes of total data and 200 partitions, each partition is a very manageable 50 megabytes. Easy, right? But if you try to read 2 terabytes of data, and Spark is still using that default 200 partitions, suddenly, each individual partition blows up to 10 gigabytes in size. A single machine trying to process that enormous chunk? No way. It's going to crash immediately.
And this brilliantly illustrates Step 3, checking for data skew. You see, small data sets are sneaky. They hide uneven data distribution. At 10 gigabytes, customer A might have 100 rows. Totally fine. But scale that up to 2 terabytes, and suddenly customer A has 700 million rows. Because of this skew, one single machine gets handed almost the entire workload. Everything else finishes up, but that one poor, overloaded task just runs forever.
So how exactly does a senior engineer fix this? Well, to fix partitioning, you explicitly increase them using the repartition command. To tackle that nasty skew, you use techniques like salting, which is basically adding random numbers to keys so the data is forced to spread out evenly. Or you can enable adaptive query execution, or AQE, which lets Spark automatically handle those skewed joins for you.
Let's move smoothly into Section 4, shuffle, memory, and resources. Now for Step 4, check the shuffle. Operations like group by or join force your data to physically move between different machines across the cluster. That movement, that's a shuffle. And let me tell you, moving terabytes of data across a network is a massive, massive bottleneck. Smart engineers know they need to reduce that shuffle before tweaking any hardware. They do this by filtering data much earlier in the process or by broadcasting small tables directly to the machines before a join even happens.
Which brings us to Step 5, checking memory. Now you can see exactly why immediately bumping up executor memory is rarely the first move for a seasoned pro. Interviewers actually hate it when you jump straight to memory. Sure, you might eventually need to tweak it, but throwing expensive hardware at a problem without actually checking your data distribution and your code first, that's just inefficient. Always optimize the operations first.
To round out our troubleshooting framework, let's look at some logical checkpoints. Step 6. Avoid bringing massive amounts of data back to the main driver node using collect.
At 2 terabytes, it will crash your driver instantly. Step 7. Check your file layout. Make sure you don't have millions of tiny files creating massive overhead. And Step 8. Verify your underlying cluster CPU and network resources.
But here is the most important part of all. Step 10. Always use the Spark UI for evidence. A true engineering mindset relies entirely on UI metrics in logs to justify every single configuration change. You don't guess, ever. You actively look for long-running tasks, data skew, shuffle spill, massive garbage collection times, and failed executors.
Let's move to and see how this builds into Section 5, the ideal interview answer.
So here's how you put this entire mindset into action when someone asks you that dreaded question. You say, when an application works with 10 gigabytes but fails with 2 terabytes, I wouldn't assume it's only a memory issue. I'd first identify the exact failure from the logs. That opening right there, it immediately proves to the interviewer that you avoid the amateur guessing trap.
Then you build on it. You say, then I'd check partition sizing, investigate data skew, analyze shuffle-heavy operations, and finally verify executor and driver memory. Just listen to that flow. It beautifully demonstrates a highly structured, step-by-step troubleshooting methodology. And then you bring it home with the evidence. Finally, I'd use Spark UI metrics such as task duration, shuffle spill, and GC time to identify the actual bottleneck before making any configuration changes. Concluding with the Spark UI totally solidifies your identity. It shows you're a serious, evidence-based engineer.
So I'll leave you with this final thought. The next time your application crashes at scale, will you guess or will you investigate? By applying this engineering mindset we've talked about today, you now have the exact framework to investigate properly, rely on hard evidence, and solve those massive real-world bottlenecks. Thank you for joining this explainer. Keep learning and keep investigating.